So one bit of housekeeping, I stuck Thanksgiving on here Wednesday just because a lot of people leave town, but it's also, you know, this class is pretty early in the morning on Wednesday. So although that's sort of not a meet day, I'm just going to write the word optional here. Like, I'm not going to teach anything that day. So if you are out of town for Thanksgiving or something, awesome. But, you know, we got a lot of stuff piling up right here toward the end of the term, right? Like, you're hopefully working on your project a little bit so that you're ready for this last day. And then we have one more thing to tackle right now, hypothesis testing over the next few days. And, you know, between those two things, you're probably going to feel like, oh, you have to do some help with some stuff. So I'm going to show up here is what I'm saying, but without a plan, particularly to teach. And if you are, you know, in town and, you know, you don't have to show up for the whole time, but if you show up and just want some help with some stuff, some one-on-one, that'd probably be good. I think you're going to find chapter 10 is our last chapter, and it's kind of it's kind of challenging. It's applying what we've been talking about with the idea of a confidence interval. So if you understand a confidence interval really well, then chapter 10 won't be terrible. If you really don't understand confidence intervals very well, then this section is going to feel pretty terrible. So point is, you know, this is a good day to get some one-on-one help. So obviously we won't meet Thursday for sure, but I'll be here this day is what I'm telling you. Come if you want. So let's see. And so what we've got to look at today hypothesis testing. And you have just a little bit of notes on my note sheet about that, which we'll get to in just a little bit. But I just want you to understand the concept. And this is why, if you understand confidence intervals, then you won't have this won't be terrible. So, concept. Do you agree? I think I'll even write confidence interval here. Do you agree that if somebody wants a 92% confidence interval, what we've been saying is that although you got, and I'll stick with the p-hat examples, where your data, where the parameter of interest in the language of MyOpenMath, if the parameter of interest happens to be a percentage, and I'll show you a bunch of examples in that in just a minute. If that happens to be the case, then we go do our study and we get a p-hat value. And we're going to do a 92% confidence interval. The key, though, is that the real p-value is what we don't know. That's what we're trying to figure out. So in the end, we might do a 92% confidence interval. And we might find that, for instance, let's say p-hat was, I don't know, 0.34. And let's say that produced an error of, I don't know, 4%. Let's keep it easy. An error of 4%. And so then what we've been saying is, if that's true, then we're saying, okay, great. Nobody ever really wanted to know 34%, but we figured out, thanks to statistics, that a little bit of error, 4%, would allow me to say that P then would be below 34% plus 4%, 38%, or maybe above 34% minus 4% or 30%. And so basically what we're saying is we're 90% sure that the real p-value lay in there someplace. And so when we make this confidence interval, when we do this, in a sense, our p-hat is really at the center because that's the only number that we know. And so we come out with these values right here, 0.3 for this one and 0.38 for this one. And we're sort of saying, effectively, there's a 92% chance that the actual population parameter, the actual population answer to this question, which is all anybody really wants to know. That's why they're doing a study in the first place, is they want to know what percent of people have a dog or something like that. And they want to know what the answer to that is. And now they're basically saying, hey, I'm 92% sure that the right answer to the question is somewhere between 30 and 38%. Now, does it make sense that in this example right here, and this is one of the main things that we've been talking about, is if you say, I want to be 92% sure, then that basically means there's an 8% chance you got it wrong. And that's fairly significant. So this section is going to make kind of a big deal about that error over there. So what we've been paying attention to is saying, hey, we're 92% sure. That's pretty cool. But do you understand there's still a chance, if you will, that we did not capture the right answer to the question? In other words, there's an 8% chance that P is either up here in this higher tail, maybe P is 40% or something, and so we just happened to do a really bad study and got it wrong, or just asked a bunch of the wrong people. Or maybe that P is over here. So that's the only change. So basically, what is this saying? There's an 8% chance that P, the actual population proportion, is outside our range. So remember, we're never actually going to know the population proportion because you can't ask everybody. So you have to take a chance, and all you're really doing is just reporting on that chance. Now, if we're going to condemn someone to death row as a result of something that we're doing, does it make sense that a person could say, you know, I don't think 8% is, I don't think that's good enough. Or if we said, for instance, on your hand-in homework, what percent of our ropes will hold up, and we said, let's do a 92% confidence interval, and then we reported that our ropes are really strong, and oh, there's an 8% chance we're wrong. Well, in that case, like again, someone goes to death row or somebody dies because your rope breaks, there are things where you say that's not good enough, and we don't want a 92% confidence interval. If we're just curious about smokers or something, you know, just about how people think in society, whether some ideology is changing in our culture, are people getting tired of wearing masks, and some percent of people are done with that, and so forth. So maybe if we get it wrong, then I don't know what we got wrong. Because remember, this costs money. If you say 92% is not good enough, let's go 98%. Does the concept that you're finding N, and you know, some of the problems we found out, oh my gosh, the error is 12%. And so I asked you on the lab, for instance, to go calculate a different value for N. And then instead of 40 people, you had to check with 1,600 people. And it's like, oh, well, that's going to cost me a lot of money and time. And so, oh, okay, this is just about people's opinion about masks, so maybe we don't care. Let's not check with that many people. So really what we're going to highlight now in this section is just what's the consequences if you screw this up and you're sort of unlucky. Your P is actually out here somewhere. So let's just say P landed right there. You know, for us, it's kind of like, oops, you know, darn, we got it wrong. As I said, if it's like people's opinion on masks, maybe we don't care. But if somebody goes to death row and we're wrong, it's like, oops, sorry, isn't kind of good enough. Yeah. Okay. So hypothesis testing is really based on this idea. We're just not going to pay attention really to what we've been paying attention, which is, hey, look, we're getting this right all the time and so forth. But you know, what happens if we're wrong? That's really the idea here. So the good news is I actually don't have anything new to teach you here. I think you'll still find this kind of confusing because of the language, and you know, you've sort of felt that, especially in the last few weeks. In all of this class, the language is really painful, and I'll try to make that really clear. But there's actually nothing new here to learn. There's nothing that we're going to do different than we haven't already done. question.
I know we have that over already, but what is that? Symbol? I can't really see.
Yeah, yeah,
Yeah.
yeah, that little fish looking unit. Yeah, what's with this thing? This is a Greek letter, and it's going to show up a lot in this section. You've seen it, you just haven't paid any attention to it because you haven't needed to. But when you were asked for a z-score on your note sheet, that little tiny symbol was there divided by 2. In other words, and thank you for asking, by the way. Yeah, it kind of looks like an A. It's a Greek letter actually called alpha, which you don't need to know. Yeah, it looks like a fish. So really, it's just somebody saying, hey, that's pretty important, that air right there. That's a really important number. So somebody thought, well, we should probably give that a name or a symbol, something like that. But what we did in the last section is we found the z-score for this, right? And did we put 92% in our calculator to find that z-score? No, we actually had to cut that air in half, that 8% in half. We had to cut that in half and realize there's 4% of it is actually down here and 4% is up there. And then we actually had to use 96% for this, right? And so that little symbol was there before as the air, the 8% air, but we just didn't really have to pay much attention to it. Well, now we're going to sort of pay all of our attention to it in chapter 10. So let me write that a little bigger. If you want to say it, you say alpha. But the name for this thing is, this is what you'll see in your homework. So I want you to understand this word, significance level. And I apologize for the terminology in this class, I really do. However, it's kind of necessary in the sense that how else do you talk about this stuff? So as I said, we're going to focus our attention on that error. So we've been noting that error all the time. We've been saying, let's make a 92% confidence interval. And we just paid attention to the 92%. And basically we're saying we're 92% confident that the right answer to the question lies in here somewhere. And so now we're just going to change our attention from the number here to the number that's left over. Really, that's the idea. So your assignments over this next, all of chapter 10, will ask you to do something with a 8% confidence level, or significance level. We're going to have an 8% significance level. We're going to have a 0.2% significance level. They're going to be using that word a lot. So, okay, let's look at some examples. So I'm gonna tell you some. I went online and I looked for like weird statistics or statistics people wouldn't believe, and I found kind of a list of like 50 of them for Reader's Digest. And one of them, said that 31% of people don't know their neighbor. They don't know their neighbors. You think that's true? It's kind of an interesting statistic, isn't it? 31% of people don't know their neighbors. Of course, you're thinking first to yourself, like, am I a person like that? I mean, you might also think, is that good or bad? I mean, it's like, is that bad that you don't know your neighbors? No. Is that good? I don't know. Depends on your neighbors, right? How weird they are. So when you see things like this in the world now, and you probably agree this isn't that important, right? Do we need to be really sure about this one? Yeah, who really cares? It's just a point of curiosity. 1/3 of people basically don't know who their neighbors are. And so what I would like you to think when you leave this class is, notice the data here, or the parameter of interest in the language of MyOpenMath and this class. The parameter of interest happens to be a percentage. It's not how many people don't know their neighbors, 17. It's what percent of people don't. And I think that kind of fits here. And by the way, this is America, if you happen to care. But again, wouldn't you assume, does this feel like what your project could be about? You could just decide, hey, that's interesting to me. I'd like to know that. And so then what do? You just start asking people, right? Again, my question is, and I hope your question is too, I wonder how many people they asked. Did they ask, well, 100 people and 31 of them said they didn't know their neighbors? So was N 100? Or was this really important to them? And they asked, thousands of people, 1,600 people. Did they do a calculation ahead of time and say, I want to be accurate to 1%? This is really important to me. And so, they did that little N calculation on your formula sheet. I want to put that up there really quick, just for you to think about. Leaving this class, I want you to be able to do something. So they decide, hey, let's go perform this. And I'm going to choose a confidence interval or confidence level of say 95%, that feels high enough. And I want an error of 1%. And I don't have any previous study that I've ever done. I've never heard anybody do anything about this. So I'm going to solve that equation for N so that I know how many people I need to ask. And then they can go ask it. Notice this study that I saw didn't say anything about error. It didn't say there's a 10% error in this study. That would have been nice to know. They did not list a confidence level. Sometimes you'll see that and sometimes you won't. So they just tell us that, and I'm left to either believe or not believe it. But again, I wonder about this stuff. Do people, are they really careful about this? I mean, it sort of feels like journalists will publish anything that will sell, right? Because at the end of the day, if you're a newspaper or somebody writing articles, it's about selling them. And so the point of this chapter is, do you doubt this? And when I say doubt, some of you might say it's too small. I think it's actually higher than that. It's like 50%. Or no, I think it's that people really, 1/3 of people don't know their neighbors. That seems really high. I bet it's like 12% or something like that. But the point is, you should doubt. Question.
How do you decide what your confidence interval should be? Because it's always different, but it's like in the 90s, but sometimes 80. Is that just based on how confident you want to be on it?
Yeah, and in reality, that's actually your choice. And it has to do with whether you care a lot. If you care a lot, you're going to say 98%. I want to be 98% confident. But the downside is you're going to have to ask 1,300 people now to be that confident, and so that might cost you a bunch of money. So you better care. Now, I sort of feel like if I'm going to, if I care enough to ask the question at all, I'd like to be able to rely on the answer. But that comes at a cost. And so, yeah, you get to make that up. I'd say 80% confidence level is pretty, that seems kind of weird. Like, why would you, it seems like it should be above 90. But I said it seems like, because I'm not talking as an expert in statistics. I'm just saying if I wanted to know, I'd like to at least be 90% sure I'm correct. And that seems good. So if I'm just curious, I might stick at 90% so I don't have to ask very many people. But if somebody's going to jail over it, well, then I feel like I'm obligated to be 98% confident or 99% confident, something like that. But yeah, it's really entirely up to you. So let's just pick on that one for a second. So let's say you do doubt this. Let's just do a little study in here really quick. How many of you think that number is actually, now please vote on one of these two. I'm just going to ask you, do you think that percent is too high or too low? I think it's too high. In other words, I think it's more like 15%.
Oh, well, do you have to know your neighbor?
That's a good question. Notice, and I'm actually super glad that you asked that, because this is a big part of doing a study. Should you define that? Did the people that asked this question define that? Because there is a lot of level to know. Do you just know their name? Or do you know a little bit about them? I mean, that's a wonderful question.
It took me 3 months to find that page.
Right. How many people think the percent is actually less than that? It's actually under that. So it's like 1, 2, 3, 5, 6, 7 of you. How many people think it's actually more than that? It's about split. Like I didn't count exactly, but you're about half of you think it's higher and half of you think it's lower. It's kind of interesting. And so if you decided you cared about this matters to me. And of course, you would need to dig into this a little bit, because you actually kind of need to know what question they asked. Did they actually just ask that? Do you know your neighbors? Yes or no? and then they just wrote it down, or was it like some big questionnaire? Because if you decided you were going to go perform this, you'd have to ask the same question. Does that make sense? So that's
It also
interesting.
really depends on where you are. I mean,
Nice.
like comparatively from, like, I lived in Arizona my
That
whole
was a
life,
great
and
point.
they're like way more antisocial than people in Oregon.
Right. Bigger cities, people tend to be less social, don't they? If you're more out in the country where you feel like, yeah, there might be a fire, or, you know, I'd like my neighbor to keep an eye on my house, at least I'll keep an eye on your house, you keep an eye on mine, that kind of thing. That's a really good point. Which again is in the bigger picture of this class, which we're really not spending much time on, is kind of where biases come in for stuff like this. Because you can't just ask somebody on Facebook this question. Because if you ask New Yorkers, you're going to get a very different answer in a crowded place than if you would kind of out in Sam's Valley, so to speak. So yeah, that's the hard part of this. Like you can put a lot of work into this and it can be kind of completely just a lie. Okay, so I want to do 10.1 is really introducing you to what at first will feel like a pretty complicated language to this. And so let's start with that. So something called the null hypothesis. So I don't know if you have a good feel for what the word hypothesis means, but if I said my cat food is disappearing every night, I think it's Bigfoot. That's a hypothesis. That's an educate. Well, maybe that's not such an educated guess. That's my hypothesis to why it's disappearing. Or no, my neighbor is taking it for their cat. Or a raccoon is showing up and eating it every night. That'd probably be a good hypothesis, wouldn't it?
Or a sneaky cat.
Or what?
Or a sneaky cat.
Yeah, your neighbor's cat. But all a hypothesis is an educated guess, and that's kind of the point here. So the null hypothesis is based, and I'm just using my own language for this. I hope you're reading ahead in your book and that what I'm saying will help you make sense of this. But a null hypothesis is just the established answer. And so again, I read that on the internet, right? That's the only thing I've ever seen. I just found it on there. They said 31% don't know their neighbors. For all I know, they just made that up. They didn't even test one person. They just made it up. Or they asked 3 people and one of them said they didn't know their neighbor. 1/3, pretty close to 31%. But that's the established answer, the null hypothesis is. And the language for that is hypothesis. So H for hypothesis, and then a little 0 down here. If you had taken a lot of math or physics, that little 0 down there just means is commonly used in a lot of other subjects than this one, and that just kind of means the starting value. So if I said, you know, I have a glucose level of 27 or something like that, that would be T with a little 0. At time 0, I had a certain level, and then I start exercising or whatever, and then maybe it changes. But that's like the initial amount. So that's used more places than just this. And so the null hypothesis here is that the people that don't know their neighbors, the answer to that is 31%. That's the established wisdom. We found that online. That's what's assumed to be true. Now, in this class, when I asked you about what you thought about that, we were almost split. Like some people, half of you said that's too low, half of you said that's too high. So that makes it, you know, like, what are we going to do now? Let's just make something up. I'll just pick this is too low. If you say that you think this is too low, then what are you proposing? If you think that's too low, and this isn't complicated, this isn't rocket science. If you say it's too low, then, well, duh, it's higher, right? It's like 32%, 34%, 38%, 90%. Like, you don't know, you're just saying, I don't think that's right, I think it's higher, but you're really not sure how much. So if you think it's too low, then you propose an alternate hypothesis. An alternate guess. So null hypothesis, alternate hypothesis. And because you thought it was too low, then you're basically saying, no, I hypothesize that it's actually higher than that. And because this is H0, then this one becomes H1. That's what you'll see, fortunately, in every question. It'll be H0 and H1. H0 is the established fact, and H1 is you saying, I don't think that's right. That's not true. I disagree. Now, to say this a little more, I don't know, kind of clearly, or maybe a little more technically. You might say it like this. H0 says that P hat is 31%. Notice I wrote 31% as 0.31, and then I wrote it this way. I did it on purpose just so that you're thinking, hopefully you're thinking, sorry, that's the same thing. So H0 is that P hat is 31%. Whereas you are saying H1, no, P hat is bigger than 31%. No alternative hypothesis. Your 10.1 questions, that's the kind of thing they're going to ask you. Now, because this person proposed it was actually higher than that, again, the idea would be, I don't think that's true, so then you're going to go perform your own study, right? You're going to go ask a bunch of people questions and try to come up with an answer. And of course, you're going to feel really stupid if you do this and then the answer to your study comes out to be 25%. Does that make sense? So what's going to happen in most of your homework questions is the only reason somebody hypothesized this in the first place is because they asked a few people and they got 40% or something like that. Like, I think that is actually higher. So you're just going to go perform a study and you probably will get an answer higher than this, according to your hypothesis. Maybe it's just a hair higher, like 32%. Maybe it's way higher, like 38%. So what we're going to talk about in this section is, do you have evidence? Is there evidence to sort of cross out the old hypothesis and say that is no longer true? The world has changed. Or the person that did this study was dumb and didn't do a very good job and they asked the wrong people or something because you went and did it and now there's like a new established answer. Does that make sense? And of course, with things that change over time, notice this starts out at H0 and then it goes to H1. Does it make sense if a few years go by, somebody might come along and disagree with you? Maybe you established a new answer to the question and then somebody comes along and now your new answer of 35% is the established answer and somebody else comes along, calls yours the null hypothesis, and then realizes the world has changed yet again. Does that make sense? So we're looking for evidence to change something established, but the point is evidence. I mean, you got to come up with some evidence. And again, in this context, this feels dumb. Like, who needs, like, why do I need evidence? Who really cares? That's just interesting. You don't really need to get this right. You don't need to be perfect about this. But if this was against, and I'll use lots of examples, if this is a rope breaking or somebody going to prison, it feels like, I should be more careful or it's more important. So main idea, let's say you redid the study and you got, say, 35%. Does that mean this person is wrong? And you're right. I want you to think about that very careful. And it's not even so much they're wrong, it's just maybe things are changed. This was 5 years ago, you did it again 5 years later, and now it's 35%. Are they wrong? Have you proven that this has changed and it's now 35%? Have you proven that? Well, the answer is entirely based on what we've been studying lately. Remember when you did your study and got 35%? Is 35% the right answer to the question? No, that's where the error thing comes in. And so what if it turned out that you got 35%, but then there was an error of 4% in your study? So you went on and did a confidence interval and you found out that your study had a 4% error based on how many people you asked. Does it make sense if you got 35 and there's a 4% error, then their answer actually could still be true and you just happen to get a higher number? Does that make sense? That's the idea behind a confidence interval. And we're going to keep talking about that. But
So for the null and alternate hypothesis, the numbers that you're actually using are always going to be the same. It's the symbol that's in between that's going to be changing.
that's exactly right. Notice these two statements from what Andrew said are exactly the same statement, but this one's an equal sign and this one's a greater than sign. Now, because this is greater than, and this is one thing that's a little different, we're going to take whatever our error is, our 8% error earlier, and we're going to put it all on that side. So because this is greater, because the alternate hypothesis is greater, as Andrew said, it's the only thing that's changed. I think it's bigger than that. Then this test will be entirely right-tailed in the language of this section. And that shouldn't be terribly new to you. It's just that like when we did 92%, wasn't there like a couple of tails over there? There's always like a tail out here on the left where this goes forever on the normal distribution. And we said in this case, there'd be 4% in that tail and 4% in that tail. Well, in this problem down here though, because they proposed it would be greater, then we're going to put the entire percent error that we're allowing or that we find acceptable. And maybe in this case, because this is just, do you know your neighbor? It's not that important if we get it wrong. Maybe we'll say, oh, okay, there can be like an 8% error. We're going to put the entire 8% error on the right-hand side of this, not split it evenly. That's the difference. So your 10.1 assignment will ask you kind of a problem like this, and they'll ask you, can you state the null and alternate hypothesis? And then can you say if it's left-tailed or right-tailed? That's really what 10.1 assignment is about. Now, let's just do some more examples. So here's another cool one. Every American, thank you. Every American produces, I'm just going to round this off. No, I'm not. Let's leave it alone. 5.9 pounds of trash every single day. You produce almost 6 pounds of trash every single day. I sort of hope that's not true, don't you? Doesn't it feel like, God, now we're trashing? It's a good argument for the environmentalist types. Let's see, trash. Okay, I bought food at the food truck the other day. Plastic fork, trash. Plastic paper box, trash. Tin foil inside there, trash. Couple little cups with this delicious yellow sauce. Have you been to Peruvian Points food truck down there? Woo, it's expensive, but good. Like all the stuff, because I got it to go, that's all in the garbage. Toilet paper, let's see what else. What else is garbage? This seems high to me. I feel like this is high. I'm hoping this isn't true, but I'm just thinking about my own life. What other kind of trash are you?
All your like kitchen trash and cooking and packing.
Yeah, cooking stuff. You go to the store, you get a bag, comes with all the food you bought. Whatever you buy, if it comes in a box, like that ends up trash. If you got a box of Cheerios, you don't throw that box in the garbage every day, but at some point it goes in there. So a ton with food. Yeah, I kind of agree with that. Is that it? Food, toilet paper, what else? Louder, what?
Amazon packages.
Oh, right, you order stuff online and you get all that junk with it, especially if it comes from China where it's got to survive a trip across the ocean. I bought this, I made my own dining room table and I bought chairs and they showed up from the other side of the world. And I could not believe how cool the packaging was because I had to put them all together, but they had it all packaged in such a way that the cardboard everywhere and styrofoam and stuff in there so that it could just get hammered with forklifts and waves and stuff. And it showed up, you know, I can totally get you. I couldn't believe it. That's amazing. But yeah, I mean, the weight of that. So yeah, stuff I buy. I mean, that's kind of, so food that I buy, things that I buy. So that's the established fact. So let's say you think that's less. You think, I can't believe that's that high. That's a lot of pounds. And so can you write the null and alternate hypothesis for this? But one of the things I want you to pay attention to is what kind of data is this? Remember we talked about the fact that there's more than one kind of data, but try this on a piece of scratch paper. You should get this wrong because I haven't taught you very much yet. Before we're done, you're going to get it right. But if you think, no, that's too high, that can't be true. That person just made that up, or maybe their study was terrible, or maybe time has gone by and it's changed. Can you write the null and alternate hypothesis? And also state, is it right-tailed or left-tailed?
So we got 5.9 an average.
Yes, that's a very good point. That is not literally five, and that's another great point, I think. It's not each person exactly is 5.9. It would be an average, wouldn't it? There'd be some trashier people than others, and it's per day. Like there might be some days where you don't really produce much at all, and then you buy something from Amazon and there's like 20 pounds of it or something. I helped my neighbor yesterday, whose name I know, unpackage this crate and was like surrounded with plywood. I mean, he had 40 pounds of garbage on that. Actually more, because it had a pallet underneath it. Probably 100 pounds of garbage. So good point, Andrew. It's like average per day, not every single day. So here's the key. Did you say this? Did you say H0 would be the null hypothesis is, did you use p-hat? I hope not, because the data here is not a percentage. You could use this. The mean is 5.9 pounds. This is a little bit arguable, but notice I have two symbols for the mean. I have X bar and mu. In a sense, it might be better to kind of call this one the population. In other words, if this is actually the established answer, then the population proportion is 31%, and you're sort of saying, no, I don't think that's true. So here, actually, I think it makes a little bit more sense to call this, since this is the established fact, came from the internet, so it must be true. Kind of like Andrew's point, I'm going to write the word average in there. So do you agree that's the null hypothesis? The established answer is a population mean of 5.9 pounds, but notice there's a totally different symbol for that. There's two questions you might ask. One, the answer is a percent. The other is it's a number. Two different sets of formulas. And we've been working on that from chapter 8 and chapter 9. I'm hoping that's sinking in. And so what would the alternate hypothesis be? H1.
Less than 5.9.
Yeah. I'm not super concerned about what symbols you pick. In other words, I'm just using mu for the mean this time instead of X bar. You're saying, no, I think it's actually less. Notice you're not saying how much less. You're not proposing mu is 4 pounds per day. You're not saying you know the answer to it yet. But right now you're just saying, I think that's less, therefore I'm going to go spend a bunch of my time and money and try to prove that I'm right about that. Is this right-tailed or left-tailed? Because this is less than all of your error, because this is what the concept of the significance level, that amount of error that you're willing to accept from the study that you do, all of that error is going to go to the side in which you say you're guessing. So because it's less than, this would be left-tailed. What about this one? One more. 11% of people, I think this is America. I didn't look super close. 11% of people have never left their home state. I think this was America. 1 out of 10 people. 2 people in this room, so to speak. Again, we have all these questions. Who did they ask? There are states that kind of feel a little more like, you know, everybody knows their neighbors. They like it there. They live next door to their parents. I sort of think of the Midwest being like that. You know, I sort of feel like Midwest people would be more likely to have never left their state. Obviously, it's a little bit of a money thing, right? If you can afford to fly, then you probably fly some. So maybe if the state was a little poorer. But again, that's kind of a surprising statistic, isn't it? And again, I would say probably everything I'm putting up there is just curiosities for the most part. Maybe the second one, like if that answer is really true, it's kind of like, man, we should do something about that. But this is just a curiosity. Like we're not super concerned about this. Again, I would ask, you know, what do you think? Do you think that's too high or too low? Probably you're like me and thinking, I don't know, never thought about that before.
I think it was right.
Yeah, he could totally think it's right. Does that make sense? It actually kind of feels right to me. I'm sympathetic to that. I find in myself thinking, I guess I believe that.
What do you want us to propose for this one?
Yeah, so let's write one. Let's say you think it's higher. Actually, let's do something a little more creative. What if you just think that's wrong? You don't even commit. No, it's not. It's not 11%. Is it higher? I don't know. It's not 11%. I mean, that's kind of a weird thing to do. This is not really very a practical question, but you will have questions like this in your assignment. I just think that's wrong, but I'm actually really not sure. And the practical side of this would be, maybe like me, you're thinking, well, that's kind of believable. If it's wrong, I guess I don't really know what direction. So I'm just going to say, this is important to me. I'm going to go do a study on it and try to see if it's actually something else, but I actually don't know how to, what is it? Is it more? Is it less? I don't know. I'm just going to go check.
Would you just say it's not equal to, just put a slash?
Nice. That's exactly right. So you're, and again, think about what kind of data is this?
Is the 11, is that a population or a sample?
It has to be a sample. I mean, at least this 11, because they couldn't have asked everybody. Does that make sense? That's why I'm saying I'm not super concerned. And we might take a look at my open math in a second just to kind of see what they're writing here. But the key is just, is your data P for proportion or percent, or is it mu for average? So in this case, because the data, the parameter of interest is a percent, you should be using P, whether it's P hat or P. So the null hypothesis, the established fact, is that P is equal to 11%, however you choose to write 11%. And you're saying, as Zoe correctly guessed without me teaching this to you, no, I can't say it's bigger or less. I just got to say it's not. It's not 11%. I'm not committing to whether it's high or low. And the problem with this is, what do you do with the amount of error? If you decide, this isn't super important, I'm just going to go with 6% error. I'm okay with a 6% error or a 6% significance level. The reason that you're being asked this question about where the tail is because you got to decide what to do with that error. If it's left-tailed, we're going to put all of our error over on the left tail and none of it on the right one. But in this case, because we're just saying we don't know, then you're going to have to put half your error at the top and half at the bottom. So in this case, it's not left-tailed or right-tailed, it's actually two-tailed.
Would it actually be P hat? Or
Yeah, realistically, I think you know, these are all P hats. In other words, wherever the person got this in the first place, that was a study, right? That's not the population. We don't know. Certainly when you go do your study, your answer will be P hat and, you know, maybe it's 13% or whatever. Let's just check really quick for the fun of it, even though it's not going to be fun. I'm just going to open up my open math and go to, I actually want to know if you kind of feel like you could do the 10.1 assignment right now. My open. Ten point one. We got to do 10.1 and 10.2 today. Let's just skip down to some random question. I don't like those percent questions. Let's try this one. So in a sense, I'm doing one of your questions for you. You'll get different numbers, but it'll be about the same thing. Okay, there's this blue catfish, whatever. The largest species, the world record is 143 pounds. Same kind of thing. Somebody proposes the largest is 143 pounds. Okay, caught in some reservoir somewhere. The average weight, though, of that blue catfish, the average weight is somewhere between 20 and 40 pounds. By the way, stop right there for a second. That should be profound to you now after this class. If somebody says the average weight is between 20 and 40, is that interesting if they said it that way? You should think something like, I would hope, well, let's see, between 20 and 40 is actually 30. And then they sort of gave an error of 10. You see what I'm saying? Like, that's what we've been doing. I'll leave it at that, but it's like they just didn't commit to what it was. And so since that catfish was caught in that particular reservoir, you think the mean weight in that reservoir is bigger. In other words, it's more than 40, like that's a special lake, has really good food or something like that. And so although the world's average may be 40, you're saying that particular lake, it's more than 40. So words that should stand out to you, greater than 40. So null hypothesis. Look at my choices. Is this P? Notice it's all P. There's no P's and P hats. First of all, is it P or is it mu? What's the data here? It's not a percent. It's a weight, 40 pounds. The parameter of interest is the average weight, 40. And so that means I should be picking one of these. Which one should I pick? I'm going to pick on people. It's okay if you're wrong. Alondra, what do you think? Which one?
Well, I know it's the mean.
You got it. The
I don't know.
H0, thank you for saying that. There's nothing wrong with that. Let's see, who should I pick on now? Samantha. Equal. To Andrew's point earlier, yeah, the first one is always going to be equal. The null hypothesis will always be equal because that's the established fact. Equal to what? What's it going to be equal to? Yeah, they said it's 40 pounds. And so, bam, I'm just cheating and saying, what's the answer here? It's kind of interesting. Notice they said the person could have put mu is equal to or less than or equal to. Why did they say or less than or equal to?
Because it's not greater.
Yeah, two ways of looking at it, because it's actually not greater, or over here, they said it's, between 20 and 40. So they just kind of pick the highest number.
Is that just a more specific way of saying it?
Yeah, I mean, I think equal makes the most sense. This is the established fact. But since they didn't just say, and they made this question a little confusing, since they didn't just say the average weight is 40, they said it's 20 to 40. That's really why they said you could put a less than sign. So what's the alternate hypothesis then? This person believes, notice they haven't done a study yet, they believe that the mean weight is, very important word right there, greater. So they're saying the mean is greater. Notice again, we have this huge choice. You should rule out all the P's because that's data that's a percentage. And so it's either the mean is equal to, the mean is not equal to, the mean is less than, the mean is greater than, the mean is less than or equal to. Notice this did not say greater than or equal to 40 pounds. It just said greater than. So do you see why that's the answer? The mean is actually greater than, and again, 40 pounds. So what kind of a test is this? Is it left, right, or two-tailed?
Right.
They're saying it's greater. So again, we're going to take all of our error, our significance number, our significance level, and we're going to put it all on the right-hand side. So the fact that this is greater means this thing's going to be right-tailed. Again, we're just looking for proof. So before we, go into actually trying to answer questions like this, the important thing to understand is the person believes this, they decided they care. So they go capture a whole bunch of fish and then find the average weight. Let's say it was 45 pounds. The average weight of the fish they caught 12 fish. They were averaged 40 pounds each. Does that prove they're right? Do you understand that their 45 was a sample mean? It was a study. And what we've been learning the last couple of weeks is their sample is not the population mean. It's wrong. So if they got 45, remember it's wrong, but it could be wrong low. It could actually be 50. We don't know. Or it could be wrong the other direction, wrong high. They just happened to catch one big fish that screwed up the whole lot, so to speak. That's the idea of a confidence interval. So if they get 45, does that prove that they're right? Not necessarily, because their sample mean, not their population mean, their sample mean of 45 could be wrong. And if it's wrong in such a way that it's off, well, by an error of 5 pounds, does that make sense? If there's an error of 5 pounds in their study, then the fact that they got 45, it could be off by 5 means that the answer could actually be 40, and they just got a high one. And so there's not enough evidence to overturn that. That's where this is going to go. Again, these examples all feel playful. They don't feel like, it's really important that I need to know this. I assume the bottom ones are harder. Let's stare at something down here. Let's look at question 6. 20% of American young people between 12 and 19 are overweight. Okay, that's the claim. But this student says his local school is in better shape than the national average, so their proportion is less than 20%. We don't know what it is, they just think it's less. Stare at these. Which one of those is true? Notice I didn't have to pick it myself. It's like I got 4 choices here. Always an equal sign. %20 is the established value. Notice the data is a percentage. Therefore, this says P equals, not mu equals. P equals 20%. Correct. P equals 20%, correct. P is not equal to 0, not correct. P equals 20%, correct. It could be the first one, the second one, or the fourth one. Do you agree with that? But then we go on. Notice they didn't call this H1, they called it, I guess, HA for alternate, hypothesis alternate, I guess. The alternate hypothesis, P is not 20, P is bigger than 20, P is less than 20. I guess they gave me every possibility, didn't they? What was this person's thought? They thought less than 20. So do you agree it's this one here? Didn't say less than or equal to. That's why there's just a less than sign. Now what's with this last statement? Suppose the result is to reject HO. What does that mean? Reject HO. What is HO? Oh yeah, that's the percent of people at their school. It's 20%. Then what I want you to understand is in the language, and we'll get into this more as we go, but the language of this is, can you reject the original hypothesis? In other words, you've now done your study. And let's say, for instance, you did your study in your school, and sure enough, you got 16% for the answer. And so, oh yeah, I got 16%. So now it's a question of, can you reject the original established fact? Can you reject that and then jump on the new bandwagon that the answer is now 16%? Can you reject that? This is the language of hypothesis testing. It's not so much can you accept the new fact, it's more, do you have enough evidence to reject the established fact? Can you appreciate, because 20%, notice it said according to the Center of Disease Control, doesn't that sound kind of like, ooh, that must have been a big study. That's a big government institution. They must have spent a lot of money and really have, a good answer to that question. So if we're going to reject that, we're going to say, give them the bird. No, that's not true. We better have some evidence, right? Because we're going to say, I want to reject what you said is true. I reject 20%. At this school, it's 16%. I can reject that. I better have evidence. So again, this is a subtle point, but it's not, you're never accepting H1. You're never accepting technically the new hypothesis. You're just rejecting the old one. It's kind of splitting hairs. So let's see, if we are going to reject the old one, then there is sufficient evidence to support the claim that the students at the local schools have a smaller proportion of obese students. There is sufficient evidence to support that claim that it's really lower. There is not sufficient evidence to support the claim that at his local school, they have a smaller proportion. There is not enough information to even answer this question. If they reject, if the result was they rejected 20%, then there must have been some evidence to prove that. As I said before, though, just because they did their little study at their school and got 16%, is that enough evidence? No, because that was a sample proportion that they did for 16%. And we know that as a sample proportion, there's actually a confidence level that goes along with that sample. And if that confidence level was big enough to include 20%, then you do not have evidence to reject it. They're saying we do have evidence to reject that. So does it make sense? Then there must have been sufficient evidence to support the claim that the students at that school do indeed have a smaller answer to that question. So this can sound a little legal, but keep in mind, sometimes you're talking about something really important. And so it's all about, you have to understand clearly that the null hypothesis is the established fact, maybe done by the Center of Disease Control. And so just because you did your little photo study in your town, on what basis do you feel like you have justification to toss out that established wisdom? You have to have evidence. And if you do, then you're going to reject the established fact. That's the idea of this language. Now, I think we're good. Let's take a 5-minute break because we're an hour in, and let's just start applying this to let's start applying this to 10.2, where we're actually gonna go get some evidence and so forth. So take a few minutes.
Yeah.
So I did it twice. But this will be the third try, so.
Percentage of milkers is 35%. It's right. It's just that that's 35%.
I put 0.35.
You did, and it still
Yeah.
didn't like it. Okay.
Yeah, so I this is my last try. I think
Yeah.
I'd submitted a few. That's what I did, put 0.35 the first time. But I didn't see putting percent in there. The symbol. And that point.
You've already put this one, is that right?
I did it with a different symbol, so I have not done that one. This could be correct. So I did it. I actually.
yeah, what did you try so
I had that
far?
done the first time
Got it.
that I used 35, and then I did.
And then
I
you
did it
put,
with P and did 0.35
got it. Okay.
because it shows both red, like they're different
Yeah.
problems. So I can give it a go.
Go ahead and say yes. If it's wrong, I'll change your grade, but I think it's right.
So it shows that, right?
Show the answer now, because I'll give you credit for it.
And maybe that doesn't.
Oh,
Or do I get full points? Oh, I have full points. So this red part isn't saying that that's wrong. It's just not grading it. Or something. Because it says I have full points.
Did you answer that part of it?
Just the drop down.
Okay. P equals, so P equals.
That part's weird. We can check mark and just that's red, but it looks like 3 out of 3 points. Just maybe it threw me off because it was red over there.
You're right.
So, but it's a point. I don't know if that threw other people off there.
This is question 3.
I believe so.
Pull that up
Check
too.
for you. Sorry, that was 5.
5.
So this is a tested, this is critical value, right?
They're both. This is if the data is a number,
Okay,
and this one, Z, is if the data is a percent. But those are both actually.
that's what I thought. So one question is a sample of that with the percentage of cat owners. So for that, that's what I would use, right?
Yes, except for not, that's not 100. Because
The sample would.
that's not a P, like this is, so
Oh,
you're using this formula and everything you said there's right, but it's like P hat minus P0, that's not P hat.
okay. So that's the only 2 numbers they give you.
No, that's not true. Let's go look.
So the established answer is 30%. But you're saying that it is 37. That's the P0. So look carefully at this. Look carefully at these 2 symbols. Yeah, whatever I have to say about it.
Okay. I think because I tried it the first
makes sense, because you're gonna do math, you're gonna do math with it if you do not do that, so.
Good questions. Okay, another crazy. Now, we're actually going to do the test this time. We're gonna decide if there's evidence to reject the null hypothesis. So let's look at this example. Another weird statistic I looked up said that 20% of Valentine's gifts are for pets. That's kind of funny. Think that's true? I love my pet, right? Valentine's Day, give stuff to people you love. So you should be able to write the null hypothesis for that just from that alone. Now notice 10.2 is just looking at percentages. Notice this says hypothesis tests for P, not for mu. All right, here, mu is what we're going to be talking about in 10.3. In other words, what if your data is an average weight, like the fish in the lake a minute ago? So fortunately, this is the concept for both the next two sections. But this, we're only going to be, every question you see will be a percent. They'll always be debating some kind of a percent. So do you agree? Let me check something here really quick. So do you agree that the null hypothesis is that P, population proportion, is equal to 20%, which I'll write in its mathematical form, because I gotta do math to this number in a little bit, and 20% is not 20. 0.2 is 20%. So I gotta do math to it, so I'm just choosing to write it that way. So again, I read it off the internet, so that must be established fact. And so you decide, you take issue with this. You think that's actually higher than that. So you think higher. And you decide to do something about it, like actually go perform a study. let's say you find that 58 people in your study, 58 people bought gifts for their pet. And how many people did you ask? You asked 187 people. You asked 187 people, 58 of them said, yeah. Whoa. What's that all about? That's better. So were you right? Notice I didn't give you a percentage. I didn't give you another percentage. I didn't say you did a study and got 25%. I made you figure it out yourself. Isn't that what happened in the real world? You're just gonna have to go ask people. I like this symbol, hence, isn't P hat 58 out of 187, which if you actually got roughly 31%. Now, if you did that, would you feel like pretty good about that? In other words, I think it's more than 20. You went and did a study, and 187 people is no joke to ask, and you actually got a number that was way higher. So the question is, so I'll kind of note this. So does it make sense? You think it's higher, therefore your alternate hypothesis, I'll even write it the way the homework did, HA instead of H1, is that no, P is actually bigger than 0.2. So there's my two hypotheses. But then you actually go do something about it, and you get an answer that actually justifies what you thought. The question is, do you have the evidence to, notice why I'm saying this, do you have the evidence to reject the established fact here? The National Institute of Pet Lovers came up with this study, and they checked with 50,000 people, and they got 20% for their answer. And now here you come along on Facebook in your backyard out in White City or whatever, and you get 31%. Like, can do you see the logic of this? Do I have enough evidence to overturn this? We don't know where that data came from, but I'm just saying that's the way you have to think about this. Do I have evidence to overturn the 20% now? Evidence. The answer is we don't, not yet, I'm not sure. Remember, 31% is not true. You agree with that? Remember when we made a confidence interval and we said, okay, well, 31% isn't true, but I'm 92% confident the right answer is between 25% and 37%, something like that. You see how this is the evidence part of this. If we're gonna answer this question, this is always the way it's worded. Can we reject? We have the evidence to reject the established fact here. Well, we got to do some math. You can't just decide you feel like it. I mean, that's kind of the key here. We've got to do some math. And so how does that look? How do we do that? Now, what you have to decide though, when you say, can you reject this, is what I said before. What is your significance level? How important is this? I hope you would kind of think, hey, we're talking about Valentine's for pets here. Like, this is not life threatening. I can be I can be wrong and it's okay. No one's gonna die. This is not someone going to death row. So let's choose a, and I want to use this word because you'll see this. Let's choose a significance level of 5%. In other words, look for this to be in every one of your problems, because, you know, on an assignment, they're going to pick this for you, right? In the real world, you just pick it yourself. In other words, basically, I'm saying if there's a 5% chance of error or less, then I'm good with that. There's a 5% chance I'm wrong, I'll take that bet. But again, in the real world, if I ask you if there's a 5% chance of something, would you do it? It depends on what's at stake. There's a 5% chance you'll die if you eat this steak. Will you eat it? Probably not, because the steak isn't that great. But if I said there's a 5% chance you'll die, but if you don't, you get $6 million. Some of you probably would take that one, right? That's kind of what I mean. That's the idea here. How important is it? We're saying there's a 5% chance we're wrong, and we're willing to live with that. Because this is just for pets, I'm thinking, okay, I would take that bet. I'm not going to bet my life on 5%. So that has to be given to us. And now we can kind of go to work. Now, because our null hypothesis was equal to 0.2, but we said, no, I think it's higher, then what kind of test is this? Is this left-tailed, right-tailed, or two-tailed? Because it's bigger, this is two-tailed, and so here's the idea. I'm sorry, right-tailed. So what does that mean? That means we're putting all of our air right over here. We're not splitting it in two and putting half on one tail and half on the other. We're saying it's all over there. So there's going to be a 5% chance I'm wrong. Okay. Let's see, I think I can say this is true. So if 0.2 is actually at the center of this and it's the right answer, and you got 0.31, does it make sense? 0.31 could be out here, you know, kind of accidentally, it's sort of too far to the right. So take a look at your note sheet. Today, we're going to be paying attention entirely to this test statistic. This is basically 10.2, and this is 10.3. You might even write this word, and I'll write this on my notes in a second, but you might even write this on your note sheet, because again, your homework assignment is going to ask you, what is the test statistic? And you're going to go, what? It's the terminology. What's the test statistic? It'll ask. Now, you should actually recognize this formula, because this is a formula we've used before. Notice z-scores and t-scores. But from earlier in this class, isn't this what a z-score is? You take your number minus the mean and divide by the standard deviation, and that gives you your z-score. In other words, how far away are you? And that's all this formula is really saying. You take your p hat value that you got by your experiment, for us that's 31%, and you subtract p0. Notice I used a little 0 there because that's the proportion stated in the null hypothesis. That's the initial, that's the truth, if you will. In the standard deviation, you're always taking your number minus the established answer and then dividing by, you should recognize this, the standard deviation. That's the standard deviation in percent land. P times Q divided by N. So let me write that down. So the test statistic. Thank you. If I was making up my own homework assignment questions here, I would not be using the word test statistic because I just say, go figure out the z-score. But you know, it's in my open math and they're going to ask this. So the test statistic, we are told, is equal to basically a z-score. What's the z-score that we're testing this against? So we are told it is p hat minus the established divided by the standard deviation. And notice what p, this is just interesting, but notice what p value are we using in our example a second ago? We had sort of two p values, the established 0.2, and then our study, which is 0.31. Those are both p values, right? But this is really p hat, and this is p0. This is the established, and the little 0 is just coming from the fact that there was a 0 over here. So, you know, which one of those are we using 31% or are we using 20% to calculate the standard deviation? We're using the true one, the one that we can count on. Remember, you're trying to overturn the evidence. So we have two p values, 31% and 20%, but we're using the established for that answer. So just like before, you take p times q and divide by all inside the square root sign. But you know, which p and which q? The one that came from the established answer. So let's figure this out and talk about, you know, what it means. Okay, so for us then, for our example, we'd say, hey, we got 31% for our value. And so the question we're really asking is, how many standard deviations is that away? How many standard deviations is that away from 20%? Remember, we said in this class from the start that if I'm 3 standard deviations away, whoa, that's outlier, that's really far. If I'm 2 standard deviations away, that's really unusual. If I'm 1 standard deviation away, that's really typical. Remember, that's what a z-score is. It's just how many standard deviations are you away. That's what we're calculating here. Remember, logically, you take 31% minus 20% just to answer the question, how many percent higher did you find when you did your study? And the answer is 11%. I got an answer 11% higher. See, that proves that they're wrong. It's not 20%. It's actually higher than that. That proves it. You subtract those, you get 11%, but just because you're 11% above, it actually depends on the standard deviation that you get for all of this. So if I take P0, which is 20%, then that means Q is 80%, and I divide by the square root of N. I divide by N. What's N here? How strong is my 31%? 187 strong. Again, do you feel the importance of that number? Because if I check with 7 people, then that number is not very strong. My 31% is really sketchy. If I check with 187 people, then I'm going to get a slightly different answer. Okay, so what does your magic machine say the answer to this is? I'm going to type this in wrong. I want you to tell me if you know why it's this wrong. 0.31 minus 0.2. divided by the square root of 0.2 times 0.8 divided by 187. So there's two reasons. I want you to stare at this carefully with me for a second. There's two reasons why I know this is wrong. You should know algebraically what I typed is not what this said. What I typed here is not what that said. Secondly, does that z-score make sense? If you get a z-score of -6, what does that mean about you? If I got a z-score for intelligence of -6, what does that mean about me? That means I'm 6 standard deviations below everybody else. Like there's nobody as low in intelligence as me. Is our number lower? Is our 30% lower than 20%? No, it's higher. We should get a positive answer for this, not a negative one, because our 31% is over 20%. We're higher than that. And we're higher by, I don't know, 1 standard deviation, 2 standard deviations. I don't know. It should be something like +2, +1, +3. I don't know, something like that. -6, that doesn't make any sense. Who can tell us what's wrong with what's typed there? So you are saying like so? No?
Don't do that.
Notice that actually didn't change anything. It never hurts to add parentheses. But actually everything in there was under the square root. And all there was multiplications and divisions under there. So although it's a good idea to add a parenthesis there just to say, hey, I'm taking the square root of everything, because isn't that what the symbol says right here? It knew I was taking the square root of everything, and the order of operations took care of it. So that wasn't it. In the order of operations, what happens first? Exactly. Division happens before subtraction. So it went 0.2 divided by this and got an answer, and then it subtracted from 0.31. Is that what this says? No, there's a giant division sign. The unfortunate thing in a calculator is you can't mimic a giant division sign. Really what you need is to finish the top and get 11% and then divide. So if you want to type the whole thing in, you do need parentheses, but you need them right here. I'm going to go take these away just because this is already a confusing enough statement. The point is, does at least that answer make sense? Whoa, that's 3.76 standard deviations above the mean. I would say now for the first time, you probably think, or you might think if you're starting to get the sense of this, it's like, for me to get 31%, if the actual right answer to the question is 20%, I'd have to be almost 4 standard deviations above the mean. That is really unlikely that that would happen if it wasn't true. You see what I'm saying? Just logically. If the right answer is 20%. Now, just as a side note, in terms of making sure you don't screw this calculation up, it's probably better just to say 0.31 minus 0.2, get an answer, and then just say divided by the square root, like you do it separately. Notice that gives me the same answer, 3.76. So write nothing down about this if you're good at algebra and you're like, yeah, I got that. Write a whole lot down if you're not. Like, make sure you can get this to come out right. So this is our test statistic. That's kind of huge. Also, just as a side note, notice if you got 31% and everybody else got 20%, is that a big deal? Well, it actually depends on the square. It depends on the standard deviation. So I just want you to notice something. Notice, thanks to the standard deviation calculation, if I did it by itself, notice it's saying it was typical to deviate by 3%. Until I saw that calculation just now, I didn't realize how crazy my answer high was. Do you understand that? That's why standard deviation is so important. If it turned out the standard deviation was 11%, then the fact that I got 11% higher is not that big of a deal. But if the standard deviation is 3%, well, man, I'm like 3% over the top of that. I mean, that's what a z-score is. Wow, all of a sudden I realized that 31 is really a powerful number now. I realize that's a lot of standard deviations away. So that's really unusual to happen, right? And as a matter of fact, 3.76, that's not just unusual, that's outlier. Like that's not just going to happen accidentally. If the right answer is 20% and you got 31 and you got a z-score for your data of 3.76, that is not an accident. So you are going to be able to reject the null hypothesis here. You're going to be able to reject the established 20% as the answer based on your study. Now, unfortunately, there's kind of two choices as to what to do here. Your book calls these the classical approach, and this makes me really mad. This stuff is hard enough without having two ways of doing it. Classical approach is to compare z-scores. So I just got a z-score, 3.76. But I notice I haven't paid attention to the 0.05 at all. I got a z-score of 3.76. But let's back up right here. What is that z-score? In other words, if you said I want 5% in this tail right here, what z-score is that? Well, you should say, I have a command that will do this. Notice that 0.05 is in this tail right here. I'll write this down, but I'm just going to show you for a second first. You have a command for that called inverse normal. What does it ask for? Unfortunately, it asks for the area to the left. And so I don't get to put in 0.05, I got to put in 0.95, right? So I put in my area of 0.95. And because we're talking about z-scores, mean and the standard deviation can stay 0 and 1. I don't have to like put in the standard deviation for this calculation because the z-score does not care. If I said I have a z-score of intelligence of -6, you don't need to know the mean and the standard deviation to know where I land. So this says, what goes with that? A z-score of 1.64. This is the test statistic. And I don't know if you're probably not watching me, but I keep looking over at my notes because I can't remember all this terminology either. This is called not the test statistic, but the kind of the critical value. So these are pretty important words. I'm going to kind of circle them, at least for your homework assignment. Again, we're trying to do this mathematically and create evidence. So compare the z-scores. So we got two z-scores here, 3.76 and 1.64. We're good with 5% error. Where did our test statistic, where did our z land? Since we established here that the location for 5% here is at a z-score of 1.64, and maybe you're not surprised by that. Remember when the tail was 0.025, this was two standard deviations. So the fact that this is bigger than that means I'd be a little left of two. Maybe you're not just a button pusher and you kind of go, yeah, that actually makes sense. Where did I land? Where did I land with this? My z-score put me on the right side of this, didn't it? Put me out here. Way over here somewhere. That's where my z0 of 3.76 landed me. And so since z0 was bigger than z, I guess I'll say z alpha, since didn't that z-score come from that 5% right there? It came from alpha. Since this is bigger, 3.76 is actually bigger than 1.64, then my conclusion, I now can mathematically reject. Thank you. I can now reject with evidence 20%. Based on my study, there's evidence to suggest. There's only a 5% chance that your study would put you out there. 95% chance when you do a study, you're going to land over here somewhere. But we landed out there in 5%. I'm saying that's too unusual. That's too unusual to not be a thing. There's only a 5% chance that I'm wrong here. And notice I wasn't barely past 1.64 in this case. Even if I had gotten 1.67, I would have been able to reject the established wisdom of 20% here. But I'm way past that. I'm double that. I'm more than double that. So again, the language of this, because you will be asked some questions about this, is not accept the alternate hypothesis, although that feels like splitting hairs to me. The language of this is not, I'm going to accept 31%. It's just that I'm going to reject the established fact. Question?
So for finding the z-score on this, because before we would, like if it was 9.5, we would do, or 0.95. Sorry. The 0.05, we'd split that by 2 and add it to the 95. Are
Yeah.
we still doing that, or are we?
No.
Okay.
And that's the idea to this right-tailed, left-tailed. In other words, this person committed from the start and said, I think this is higher.
So it's,
So you're taking all of your error and giving it to the high side instead of splitting it.
so if our significance level was 0.01, we do inverse norm 0.99.
Correct. So you're not cutting it in half here. We need to do more examples.
Where you say that we're comparing the z-scores by the language of my math, we're comparing the test statistic to the z-score.
Yeah, so in my open math, rather than just saying like one big broad question, like can you reject 20% and then just saying it's like a blank piece of paper, they're going to ask you for kind of some of the steps, which is actually good for you because if you get something wrong along the way, then at least you kind of know why you're wrong. So they're going to ask, a lot of your questions are going to ask for these two numbers. They'll ask for this. Tell me the test statistic, tell me the critical value, and you should find yourself like me needing to look at your notes like, what the heck was that again? For a while until you get it memorized. So if I can write those two numbers down, then I just compare them. I got to know them to compare them. Oh, okay, cool. I wrote them both down. I compare them. Critical value, and there's some relevance to this language. Critical value is like, this is the important number. I got to be outside of that. I got to be in the tail. I got to be in this critical area over here. I got to be in that tail in order to reject this. So that's the critical value. And then what did I get when I ran my test? I did a statistic. I did a test. I went and did my test up here, checked out some people, got 31%. And so what z-score did that test produce? Oh, this z-score. And now I can compare those two z-scores. So the classical approach is compare those two z-scores. really, what does this mean? It just means the test put you in that tail, that tail defined by alpha, kind of puts you out in that tail. There's only a 5% chance it would be out there. Only a 5% chance I'm wrong. I'm sort of willing to say, all right, I'll go with that. You may also see this place, but along with the critical value, this is kind of the critical region. You might see that terminology someplace. I'm not super concerned about this, but I think I saw that on one of your homework assignment questions.
Would it change if it was left tail? The value, the value?
Yeah, see, the key is, does your z-score land you in this critical region? And what Andrew's asking is, what if I was on this side? What if I was doing something where I was on the left-hand side? Does that make sense? Really, the question is, does your z-score put you in the tail? If the z-score puts you in the tail, puts you in that critical region, the test puts you into that tail, that critical region, then I'll just simply say reject. You can actually reject, really rejecting HO. You're rejecting the established wisdom. Now, there is another slightly different approach, which is almost the same thing. And you will see both in your assignment. So I'm showing you this apologetically. So unfortunately, this isn't terribly different. So what do we do in the classical approach? We compared z-scores. We got our z-score, and then we said, oh, that 5% is not a z-score. I'll turn it into one, and then I can compare those two z-scores. The p-value, p for probability, we're just going to compare probabilities. Well, does it make sense that alpha equals 5% is already? It's already a probability, right? I'm saying I'm going to have there be kind of a 5% chance I get this wrong. It's already a probability. So the question is, can I turn 3.76 into a probability as well and compare the probabilities? And the idea is this: if you said, hey, I have a z-score out here of 3.76. Notice I didn't draw that out as far as 3.76 would be. It'd be way out in the tail, way out there. Well, what's out there? What's that area out there? So back here, maybe I'll write down what I typed earlier for this. To get this number, we typed inverse. Now I'm all confused. Inverse normal. We typed inverse normal with 0.95 and 0 and 1. And we did inverse normal because we knew an area, but we didn't know the score. That's what inverse normal does. Whereas down here, I actually know the z-score, but I'd like to know the area. What did we use for that? We used normal CDF. On our calculator. What did normal CDF ask again? It asked for an upper and a lower location. Well, notice because of the shading I did, my lower location is 3.76. What's my upper location? How far out there do I have to go? I don't know, way out there, 100. A z-score of 100. Doesn't that seem high enough? Now, because a z-score has a mean of 0 and a standard deviation of 1, I could just leave those alone. So that's what I'm typing. Let me write that down and then we'll do it. 3.76. I don't know, 100, leave 0 and 1 in there. In other words, what area does that produce? It produces an area, woo, that is a small probability, a small percentage, a small answer. 0.040 and then an 8. So 5%, what did I get? Where did that put me? Change colors. If the probability that you got based on p hat, which is that 0.008 we just got, if that answer is less than the 0.05 answer, then you can reject. Sorry, I'm running out of room. We need to do one more example and then do you find that annoying? It was like 2 different ways. Like, just tell me one. This is already hard enough. I do. On a test, I'm actually not going to ask you to pick. I'm not going to say with one question, use the classical approach, and with another question, use the p-value approach. You will have to do both on your assignment, and they won't even use that language. They'll just ask you, and I'll show you this. What time is it? I'll show you this in your assignment. They'll just be asking you for some of these questions. Does it make sense? They could ask you for this p-value. In this example above, they're going to ask for the critical value and the test statistic, and then they just want you to compare those two. So they're not going to say, use the class. You'll never see this in MyOpenMath. They'll just ask you for the critical value and the test statistic, and then they'll ask you to, is there evidence to reject the null hypothesis based on that? And you'll say, oh yeah, I got a bigger answer than this, and so then I can reject. Or what would they ask if you were using this p-value approach? Well, they'll ask for that p-value right there. They might ask for your, what was that thing called again? What's that 0.05 called? They might ask for your significance level, 0.05. And then they'll ask for your p-value, probability, in other words. So 0.05 was already a probability, and they'll ask, what was your p-value? And then based on that, you can say reject or accept. All right, this feels to me like that's it, but feels like we just need to do another example. Don't you feel that way? What I'd like to do this time is introduce another question, but then kind of give you time to try to, I'll put my original note back up there. I'll just give you time to like screw around a little bit rather than just immediately do it. Let's see. Here's another weird statistic. I'm not going to write this out completely, but I don't remember where I found this, but this one actually I find interesting for some reason. A banana is actually 65% fruit. In other words, you buy a banana at the store, and roughly 2/3 of it is actually the part you eat. Anybody eat the peel here? Don't want to hurt anybody's feelings. Now, of course, that's a little interesting just because you pay for bananas by the pound, right? So you're actually paying for the entire weight of it, but then you're only eating 65% of it. But again, isn't that interesting? Because doesn't that seem like there'd be variability? Like, wouldn't you have some bananas, either some varieties of banana, or maybe some countries where the skin would be thinner than others? And so can you appreciate if you went and weighed that on one banana, you're probably not going to get 65%, but based on the fact that that's out there, I found that online, that's probably reasonably close. It's probably not 12%, it's probably not 90%. I bet I would get something in the 60s.
Is
So
it the weight or the actual?
another
peel to-
excellent
peel
question.
to fruit ratio?
That's another excellent question. There's two ways you could measure this. One would be volume, like you dunk the banana into water. And so it's 65% by volume. This particular one I know is by weight.
I would think you'd have to measure it at the same distance from like in of time from it being cut off the tree.
Yeah, that's interesting too, because the thing starts to rot. So does that make a difference? And to me, what would make this class fun is if we had time to not just, talk about this kind of stuff, but go do it. And it would double the amount of time it took to take this class. That's why we don't do it. But I read stuff like that and I think that's kind of interesting. And then I see the sun is shining outside and I think, well, I'd rather go for a walk. It's not interesting enough to go weigh a banana. Okay, so to do a different example, since last time we said, no, we think it's larger. Well, let's do the opposite this time. We think it's less. We think less. So we do something about it. We go, I don't know, let's go weigh 38. Let's go get 38 bananas. And I'll save you a little trouble this time and just say, okay, you went and did 38 of them, and you actually found an average that was indeed less. And we'll say you found 62%. Now notice this isn't very much less. Like last time, it was 11% higher, and so that sort of felt like, wow, that's really high. This is only 3% less. And so remember, though, the important concept here is that was just those 38 bananas. And as some of you pointed out, it's like, well, it depends. When did you take it off the tree? And also there's all the details, like the stem that's on top, you can actually cut that part off and it's still encased in there, right? So if you're a cheapskate, you got your pocket knife with you, snap off that little top, save yourself some money. So how's the top cut off? There's all kinds of, questions here. But you need to understand that p hat is not true. That is not the population proportion of all bananas. That's just your tiny little study of 38 of them from one store. And so is there enough evidence here to reject 65% as the established value for the population proportion of kind of all bananas, assuming people did that kind of nicely and so forth? So you did indeed get an answer that's less, so good job. You were right. Your prediction was true for your little study. So can we reject? That's the question. Can we reject the established fact? So your questions will all ask all of this stuff in a bunch of steps. And so they'll say, can you list the null hypothesis? that P is actually equal to 65%. And you come along and say, no, I think P is actually less than 65%. So because it's left, important to note, this is left-tailed. So why can't I say now start? Why can't, what have I not told you that you need to know in order to actually do what we just did? So the question is, can you reject 65% is the right answer in favor? And notice you're not saying it is 62, you're just saying it's less. You know that 62 is not the right answer. You just think that's evidence that it's not 65 and it's actually less than that. Maybe it's 64, maybe it's 63, maybe it's 61, but it's just less. You're not saying it is 62. That's the concept that you need to understand. It's not fair to say it's 62, especially because you only checked with 38 bananas. That's why the language of this technically is not accepting 62% as the new answer. It's just rejecting that 65 is the answer in favor of it actually being less, but you don't know what the answer is. What have I not told you that I need to tell you though? A significance level. So let's say you decide this is really important to you. Bananas are you're a monkey. This is your favorite food. So this time you need to be more sure. Last time it was only 5%, but this is important to you. So you take it down to 3%, or maybe 2% or 1%. You're always going to get smallish answers like that. You probably never get something more than 10%. It'll always be at 5% or 2%. By the way, I think I remember in your assignment, you can even get one that's 0.005, which is half of a percent, which seems like you should save that for something really important. Do you notice that our last problem would have still been rejected even if the significance level would have been 0.005? Even if you decided it's really important to me not to screw this up. I want to get this Valentine's pet thing figured out. So I'm going to pick a way smaller number, like this still would have been evidence. So again, draw a picture of this. Because this is left-tailed, that means all 3% are down here in the left tail. Let's see if we can do this both ways. Compare, I'm not even going to use the terminology this time. Compare z-scores. Second method, compare, I'm just going to even write it like this, compare percents. In other words, p's, compare p-values. Compare z-values, compare p-values. They both work. Either way, no matter what you do, you need to make this calculation. So you've got your note sheet out. You got to make that one right off the bat. So that was our test statistic. So let's do that up here. Test statistic. Let me give you a second. See if you can pull that off.
Can you show us all the values at the top?
Talk to your neighbor. I'm writing it out. (62% minus 65% divided by the square root of 65% times Q, 35% divided by the size of the sample, 38. Much smaller sample than last time. As I noted before, for simplicity, it's probably easier just to say 0.62 minus 0.65. Again, all that's establishing is just that, what did you get? Oh, you're 3% under. You got an answer, your banana was 3% underweight. The negative is under, the difference is 3%. But the question is, how surprised, how much is that off by a lot? Well, we got to divide by the standard deviation to find that out. Divided by the standard deviation, which is 0.65 times 0.35 divided by 38. I got negative 0.3877. I'll call it 0.388. Your homework assignment, sometimes they'll ask you to round to 2 places or 3. Fine, whatever. 0.39. I'm just choosing to round to 3 places. Notice that's not a very big z-score. That's not like a z-score of 2 or 1.9. It's a pretty small answer. Sort of, again, it already feels like this is not going to be enough evidence. Even though we got a smaller answer, and it wasn't insignificant. We did measure 38 bananas. That's quite a few. But man, that is a tiny z-score for what we just, it's not off by very much. Again, just out of curiosity, I'm not going to write this down, but what is the standard deviation? Oh, 8%. My study was so small with only 38 bananas in it, the standard deviation was 8%. Again, doesn't it already feel like if it's typical to deviate by 8% and you only deviated by 3, like this isn't that weird at all, is it? Last time it was really crazy how much of an answer we got, how much higher it was. But this time it's not different by much. Especially now that we know the standard deviation is like 8. But anyway, we got this test statistic. So we got a z-score, cool. We got a z-score for our test. That's why it's called a test statistic. But we're going to have to get a z-score for this alpha number. We need, at least to compare z's, we need that z-score right there. Again, I'm just going to call it z alpha. What's that z-score right there? So wouldn't I go inverse normal? And notice the area to the left is 0.03. Like I didn't actually have to subtract it. Last time it was 0.05 and we had to put in 0.95. This time I can actually just put in 0.03 and 0 and 1. I got negative 1.88. So the important question here then, when I compare these two z-scores, is where did our z-score, where did the test z-score land? This is, remember, as far as the language of your assignment, this is our critical value. This is the important division. The question is, where did we land? Did we land here where we get with mathematical justification, we can reject HO, we can reject 65%. Here, did we land here where we have to sort of fail to reject? You can't, there's not enough evidence to reject. Where did we land? We landed more like here, didn't we? We landed there. So we did get it, and this is this is probably the important part of this whole discussion. We did a study and got an answer that's lower. Can you see how somebody would, their first thought would be, oh, look, see, I checked it out and it's lower. See, I'm right. But we're using the language of the fact that samples like 62%, samples are normally distributed. That's why we keep using this example. This is just one sample. We know it's wrong. And so we have to land way out here in this little tail in order to kind of have evidence that this number is significant. So basically, if the established number here is in the center at 65%, then for you to get 63, that's not that far off. We're not out there. So 0.388 is not in that tail, in that critical area, it was called. It's not in that critical area. So we have to conclude we fail to reject. We do not have evidence. We do not have enough evidence to kind of prove that 65% is wrong. You could easily get 62%. If 65% is the right answer, you could easily go do a study with 38 bananas and get 62%, and that would just be one of those variations that we've been talking about lately. So you don't have enough evidence. It doesn't mean you're actually wrong. The right answer could actually be it's less than 65, but your study didn't provide enough evidence to do it. Not going to do this, but as a side note, does it make sense if you checked with more than 38 bananas and got that answer, like maybe 300,000 of them or something? Then maybe that would be evidence, because that makes your number something more solid. That's the idea. Quickly, what does the compare P approach mean? Compare P values, compare percentages. Well, you already have that alpha is 3%. It's already a percentage. I don't have to do anything to it. But how do I turn my Z0, which was negative 0.388, I got to turn that into a percentage as well so that I can compare percentages. That's what this method is about. Up here, we had to take 3% and turn it into a Z value. This method says, I don't want to leave, I just want to leave 3% alone. Okay, well then fine. If you want to live in percent land, then you're going to have to turn this Z score into a percent. So you should understand that for Z scores, the mean is 0 and the standard deviation is 1. So because that's negative 0.4, then I'm basically right there. I'll call it 0.388. That's right there. And I'm interested in, what is that area right there? Since it was less than, I'm interested in what's that area. So that area is normal CDF. My lower limit, notice this goes forever, so I don't know, negative 99. My upper limit, negative 0.388. Standard deviation of 1, mean of 0. What did I get for an area? 35.35. So we said in order for this to be rejected, what did we say a second ago? We squeezed it into the corner in the bottom. Your probability that you just got has got to be less than the error that you established in order to reject. So the question is the probability of the p hat you got actually less than the alpha? So is 0.35 really less than 0.05 question mark? No is the answer. It's not out in that tail. Not way out there. So again, same conclusion. You don't get to reject. Not enough evidence to reject the established fact that bananas are 65%. Now, we've been sitting here way too long. You shouldn't be great at this yet. My advice would be start wading into this. Tomorrow, I'm not going to teach you anything new. What I'd really like to do tomorrow is probably say a couple of things about this, like do one more example, and then give you time to work on your homework. Your 10.1 homework is due Sunday like normal, but I changed the due date of this from Sunday to Tuesday night so that we have a little bit more time to kind of ask me questions. Ideally, we'd still maybe get done Sunday night, just because we do have to talk about what does this look like if your data is a mean. But this is a lot to get your mind around, so long day. Get out of here. Go think about that. Stay after if you want to ask any questions as usual.
I got a quick question. So one of the problems we're talking about, this, that's not. Not.
Yeah, they're not committed to.
So they're asking if we were to, area on both sides. Maybe. So I asked. That. If I accept it. I guess that's fine.
I think we can tell you the 1% discretion. After that, oh, we would-
Critical value. So I can do that.
yeah, you can choose.
But if I was figuring it. Anyway. Left. And then. Okay, figure that out.
So we can 915.
Okay. All right, that's fine.
We have established value. Our percent value. This one's used like the full value of that. So like
what you tracked here is exactly where it is. Why'd you put 51 here? But did you put the parentheses that's squared around the whole thing? Yes.
I did.
Okay, yeah, I was actually sort of reading this before class today, but so, yeah, let's make sure.
Okay. I just want to-
You got 1 month closer.
So tell me about that number. Correct. So what's the formula for that number?
Right, this one.
Equal to n.
So ends in the 5.5.
It's the sample size, it's not the ones that met your criteria, so for the sample size. So you're doing it right. You just put it in there, and in the end, before you should get the same answer as soon as you change that. So notice this is proposing that it's actually bigger, which puts the drawing of that. It's over there. It's bigger. So you but it should be that the lower value should be this and the upper value should be that big number. I think that's so that actually is. Because you go into the trouble of doing one of these stuff. So is that number different than what you did before? That is, you can try it. No. Now, it could be 0.0038, the only my only concern is, I think, because they said around this, the 3 decimal substitute, we're assuming you're gonna use that, that's actually not a bad answer. No, that's right. No. I hope you mark it. So that's that number. Compare that with- Because you took the trouble to turn it into that, you compare that, is that put out in the tail or not? So you're concluding the objective is correct, it's in the tail. Insufficient evidence for that. Rejection will become the population proportion. You're rejecting the population proportion to be greater than 50. So you're actually something wrong. And then I hate this kind of question. Because your number is in the tail.
Yeah.
Then you have evidence. So anything that says not sufficient evidence without even reading it. No, it's not what that's saying. It says there is sufficient evidence to warrant rejection of the claim that the population is greater. You're not gonna reject that, you're accepting that. You're not rejecting that, you're actually accepting it. So the sample data support the claim that the population proportion is unequal. Do you understand what you're wrong with the other one? So that's the third trial. Do you understand why the point zero zero three seven?
Yeah.
That's slowly starting to put everything going.
You gotta draw a picture of this stuff. Like, draw the left tail from down. This problem is saying you're thinking it's less than 0.7. Right? What does this look like? It's left tail, your little area is becoming a little area on the left tail. So the point is, this is going to be a 1.7 location. So you're looking for that. Just be more careful, like, what you put in for moments to do that, but what defines that? Like, that's not the left side.
But you're going with that. What I did was everything like this now, so you can go with it.
That works. You're like getting the wrong answer and then put some.
So we do want.
Now, then if you're comparing B values, then you're looking at that percent, and then that percent. Deciding is this number fits you up? Question? Yeah. What's the actual review? What? Acres. Yeah, that sounds so interesting. Is that local? Like a-
You gotta be like.
Whatever it takes to get 31 numbers.
Right, so I put this, I mean, I could get all the data from this last year, because it's. little better to what we have for- I could do that, but each bar would be the average of that year.
Right.
Which was.
One of the things I was, I was gonna say, comparing 2 years. would be kind of interesting. Like, not even all 5, although that'd be awesome, but I just want to make sure. Might be interesting enough that you want to go out. You compare like the oldest year to the most recent year, so that your argument can be good numbers.
Right.
More stuff.
And it's not also a couple of years. It's not like 10.
Yeah, I think a couple years would be kind of interesting. If you get, keep it low, like for the 30 for 1 year. You should do them all the time.
Yeah, and
The average.
and the way they present the sizes. It's kind of easy on that, because it's all numbers, and our first year, they just have to really come in.
Are those tenths of an acre including some, in this whole guy's backyard on fire?
So, like, yeah, some of the little ones are like. Yeah, people are having shed fires in their backyard.
Or does it have to turn into a forest fire or is it just?
We
a burn?
classify it as. Well, the other. Like, through all those little ones,
Yeah.
just like the big wildfire.
That's what's so interesting about this. It's like, that's why people say statistics lie, because even if your intention is good, you still, what you find interesting is what. And then, you know, to say the average, you brought all the little ones because they're boring. You know, then you say the average fire size is 20 acres, well, that's not true.
Right, like almost every day, like, almost every other day, there was something, a little fire on the street. They will be classified as a fire.
Well, you know, if I live in town and I start a fire and burn, then that's down, that's really different if I live in the field. Also, I don't have my own property, then I'm just kidding. I'm burning the land, I'm burning your land. It's my other people. That's a total. Something that's interesting. In the end, it's not what I'm interested in. That's what I'm grading, you know, take whatever management gives me and say, did you function correctly? I'm not going to judge your decision making, but try to make it interesting to you.
Yeah,
But see, that's part of the reason I want to, you know, it's not fun, because to say I chose to, and then you say that you chose, that's not interesting. All those really.
yeah, because there's a lot of smaller ones.
Yeah.
A lot of little ones. And then there's very few. There's also
I don't know. Don't have too much data, but you end up with like 400 data points on your.
Thank you.
Question?
It's still doing the same thing. You might have to change it.
I forgot to turn off this Zoom.